This meeting is being recorded. Let's see, I'm gonna minimize here and find my other note that I had. I had some notes to myself about how we're gonna try to start doing this. We'll iron out the kinks as we go along. Again, we're all in this together, yay. We can do this. I wanted a quick little show of hands. How many people are going to write as I'm writing, like you're taking notes at the same time?
Me.
Raise your hand. There's a little like raise hand tool in the something or other, or thumbs up. That's fine. Either one.
Where is it?
I can hear participants.
If you go into participants, there's a thing that says raise hand.
Okay.
I'm gonna have a double screen, so it's okay for me.
So basically, I couldn't tell. Oh, there's a bunch of me's getting typed in. That's cool. All right. So that's why I got the computer. I got the desktop running the chat window, and I've got the laptop so I can write notes. Okay. So the one thing is, why can't I share? There we go. The one thing is, I noticed in my Chem 121 class that what I will end up doing for writing these notes is I will zoom in, maybe not quite that far, maybe something like this, so that I can write a little more legibly, hopefully, a little more legibly. I don't know if that's legibly or not. Oh, I can even erase that E, and I can make a new E. E. And then what I'll do is I'll zoom out a little bit so that we can sort of see the bigger picture.
Okay.
So, Annette, you're back on your webcam. You know what? I'm done with you. You just put my
No. It's just when I'm not on the web, I can't see. It's just a black screen.
You're not seeing my mirroring of my OneNote? You don't see me writing stuff?
Like right now. So I'm not in the video. I'm not video, but I can't see. I just have a black screen on my phone. But it's okay. I'll listen and I'll figure it out later.
But if you have your video feed going, you can see my writing on the screen.
Lynette. I will take a picture of the notes and send them to you after this is done.
Okay.
No, as I told everyone, I'm going to make a PDF of everything I've written and post it.
Okay.
So everything that we write will be in a PDF at the end of everything. Now,
okay.
And also you can actually do it.
And then I'm also going to, once I figure out how, I'm going to post the video as well. So while I'll have some static notes going on, and you'll understand what I mean by the static notes, I'm going to build an entire big diorama of some intermolecular forces here in a few minutes. And the video will capture that, but the notes won't. The notes will have it as one gigantic picture. So it might be nice if you have the PDFs and the video sort of side by side as you're reviewing the lecture. That might be something, or even, retaking the notes if you watch the video a second time. So I will be making a PDF of everything that I have here. I will be posting that probably sooner than later because I figured that out last night how to do that. The video I'm still working on, but hopefully I'll figure that out soon. So if anyone actually knows how to YouTube out there, hit me up after the lecture. Let's see, what else? Always slow me down. So if I'm going too fast or if I'm zooming in and out too fast, for those who are taking notes, please slow me down. Trying to take notes is still the best way to go about this. But I understand that if at a certain point you're like, forget it, I'm just going to watch. And let's see, no videos, no video feeds because I just don't have the bandwidth out here in the sticks to accommodate that. And the mics, I guess if you're really quiet, it won't take up bandwidth, but otherwise keep yourself muted until you want to ask a question. And by all means, just unmute and jump in like you would in class. Don't raise your hand. I'm probably not going to see it, even though I have a chat window open. I'm looking at 3 different screens at once. So just jump in and start screaming at me like you would in class, so that we can get the questions answered. This is I'll tell you right now, this lecture is basically not found in your book. So you'll want to pay attention very much to what I write here. Let's see. Again, sloppy handwriting, let me know. As we go forward, when I do some math stuff, I want somebody else on the back end with a calculator to make sure I'm getting the right numbers. There's no numbers today. Do we have any questions before I do that? Oh, somebody asked about homework earlier before I was recording. I don't see a good way of collecting homework. So it's on your own peril if you don't do it. As I said in one of our earlier practice runs with some people, someone mentioned they could make a video of themselves flipping through their homework to prove they did it. And I said I could think of better ways to kill myself than to watch 70 videos of you guys flipping through your homework. So I don't think that'll be productive. And someone asked about the exams. I'm sure you're all wondering how that's going to work. Right now, it looks like we're going to have a multiple choice for the next exam. But yeah, I'm trying to figure this out. The problem is you guys have to draw a bunch of stuff, and I don't know how to. I don't know how to go about that.
What if you drew it a couple different ways and then we had to pick which one was correct?
Well, and that's an idea. The other that someone suggested was, what if I had you guys write out your work, take pictures of it, and submit that? So I mean, it's a lot of pictures for me to go through to see the work. See, this is the hard part. Everyone is like, oh yeah, this is great, we're going to go online. And I'm like, yay, what about labs? And then what about things that have to show a lot of work? This isn't like some other classes where it's like, pick the date at which this war happened. You know, it's very difficult. So so Vince says they are doing photos of the homework.
You could put them in a PDF file so they all stay together.
Yeah, that's another question. I mean, is everyone well versed on doing that? Making PDFs of their stuff?
We could do a little tutorial. And actually, I sent you a free PDF maker where you could take different sheets and put them all into one PDF.
Oh, is that what you did? Is that what that link was?
Yes.
Okay.
Like Power PDF.
Okay, maybe I can put that in the module so that people can figure out how to do that. So I think maybe that's what I'll have to do is, in order for this to kind of work, we may have to actually just take the test and then have you guys take pictures and make a PDF and send it in. I think that's probably the only way to try to get, you know, partial credits here and there. Right.
Hey, I was looking online.
I just learned about this submit assignment thing. That way it goes into just your little folder, so I can click on it and watch it. Somebody just showed me that yesterday. I'm getting ramped up on Canvas very quickly. So, but I think that's probably what I would do, is make it an assignment, and then you guys would upload your stuff. Ostensibly, we're supposed to take this Wednesday. I'm still thinking that we can do that. What I'd probably do is, there's supposed to be a way in Canvas where I can upload the assignment, and I can make a time limit on it. And when you guys open it up to do it, you'd have X amount of time to finish it and then submit the assignment. So I'm going to go ahead and maybe try that this go around. If this fails miserably, we'll figure it out. Again, you know, if I go back to like a show of hands, how many people here have actually taken an online class? Morgan has, Stu has, so not that many, it looks like. Janet has. So, I mean, and of those like 3 or 4 that had their thumbs up, how many of these like tried to do this live stream thing? Only a couple.
I've never seen it do live stream.
Yeah, that's what I'm finding. My Chem 121 class had a lot of people who've taken online, but nobody did a live stream. It was all just like prepackaged stuff, and I'm trying to live stream so I can get the interaction, so I can try to answer questions as they come. If it works, I would like to do this. If it becomes too cumbersome, then maybe I'll just do vignettes and post them. But I'm hoping this will work. Oh, someone apparently has a camera on.
Angela, cut your camera.
Massey,
Yeah.
turn your camera off.
Sorry.
There you go.
You're
No,
good.
that's fine. So I think as per I think it was Vince. Let's see, what is it? I took a French class online, but live stream was just a one-on-one. Yeah. So you know, I do plan to do office hours via the Zoom, so we can have that kind of thing. Someone says the CFS had the option of taking the exams on Canvas. Just do a multiple choice with a time limit. Yeah, I agree, Nathan, but you know, again, we're drawing shapes, so I'm thinking that maybe I can do I could just upload the test and just give you a time limit. You guys could take pictures and make a PDF and send it back. Because otherwise, I don't know how to give any sort of partial credit if you guys were almost there or something. Like, you know, for instance, resonance structure. Did you remember to do it or not? Type thing. You can use Respondus Lockdown Browser for free. What is that, Gerardo?
It's a way that my online professors would give us our tests. So it locks you out on your browser, so you can't, you know, go in and out. And they set up time limits and everything, and they send it through us through Canvas.
Really?
Yeah.
Interesting. I'm going to write that down here real quick. All right. So it's Respondus Lockdown through Canvas. Now, which class is CFS?
No, that was the class I took at Solano.
Oh, dang it, at Solano. Okay.
Mm-hmm.
I was hoping it was here so I could not track down that prof and find out how they did it. Someone said we took the same CFS class. We had a test online. They were timed. Who was your CFS person?
Mine was Chris Guerrero, I think.
Dude, don't know. Howell. All right, I can look up Carrie. Cool. Yeah, did I say this Wednesday? That was what I was currently thinking, but with these ideas that you guys are giving, I may have to rethink a Wednesday exam and maybe push it off. If I did that, however, what I would like to do is if we do the lecture today and do not test on Wednesday, but maybe push it to Monday, we would have to go into the next section of the lectures. So I wouldn't want you guys to get confused, but I can't lose a lecture day just because we're going to push an exam. Show of hands in my little window over here. How many people are okay if I have to push it out to a Wednesday? Oh, let me see if I can put hands down here. How do I put hands down? Or did you guys all raise your hand? Yeah, everyone take their hand down real quick. So there should be like a take your own hand down. How do I do that? Oh, maybe I can't do it in that computer. Maybe I have to do it in this computer. Hold on.
There's a yes. I put the yes button.
Oops, what is this? No, don't want to do that. What did I just do? Unmute, lower the hand.
There's a yes selection, and those ones want to say they can press the yes selection.
All right, so I'm learning how on my thing over here to hopefully stop it. That's weird. All right. Hey, all this technology. All right, let's see. All right, so now that I've basically lowered everyone's hand, show of hands, if I postpone it till Monday to try to figure the better way to do the exam, are we okay to move ahead and just not include that on the exam? Looks like I'm getting, all right, you guys look like you're okay with that overall. I'm getting a vast majority. Okay, so why don't we go ahead and take the pressure off of ourselves to try to cram this thing through. I'd rather do it right than do it sloppy. So the exam will get pushed till next Monday. I'm gonna look into a way of this, respond us maybe so that we can have a timed thing. Oh, Brian Larson, I'll talk to Brian. Thank you. And then maybe, so we'll do it Monday. And I'll find a way to post it so you guys can take pictures of it and upload that as your assignment so that I can grade it and give you an exam on, or a score on that. I don't know the best way to mark it up so you can see what you did wrong. So unless somebody figures out a way to tell me how to do that, then basically you would see your grade, and I got to upload grades on Canvas. If you don't like what happened on your grade and you want to do an individual office hour so you can figure out what went wrong, we can do that.
Send out a key later.
I could send out a key later. Yeah, I can do that. Will the call be Angie? I have a presentation Monday at 9:30. Yeah, I mean, everybody said they wanted the lectures a little bit later, like 9:30. That's the reason why I was doing that. Do we have to go back to an 8 o'clock for people? Or are you okay doing the, are you talking about the exam, Massey?
Yeah, Monday.
Oh, yeah, no, so, yeah, I like sleep, I get it. So the exam, I would basically say that I give a time window, I guess, to take it. So you wouldn't have to start it at 9:30. I may make a larger time window. You're just, as soon as you start it, you'd be timed.
Oh, okay. Thank you.
Okay, everyone is like freaking out. Oh, and Carrier. Since I'm her lead coach, she owes me one. So I can talk to them to see how they do it. Okay. All right, do we have other burning questions then? So before anyone, what topics are we being examined on? Winnie, come on. I'll tell you all that just at the end of this lecture. You know me better than that. Any other burning questions? So homework, I'm just going to assume you guys are doing it. I don't know a good way of collecting points or not on it. So we're just going to cut homework from here out as part of the grade. Labs. Okay, let's talk about labs. I don't know. Has anyone checked the module to see if the experiment 6 has gone live yet?
It has not.
It has not. Okay, I will look to get that live. So what has happened is Dr. Hansen and myself went through, we did the labs, performed the experiments, we took videos and or pictures and have created a sort of virtual lab for you guys to do. If it's not up yet, it will be very soon. What I'll expect is that you guys run through the PDFs that are up there to sort of show you what's going on. You guys can do the pre-lab, the post-lab, and fill in the data sheet as though, from the data that we gave you. At that point, you can take pictures and upload the assignment so that I can look through and grade the lab and give you points. Can we revisit homework if we find a solution, i.e. scanning to PDF? Homework is super helpful. Yeah, I get it, Reagan. Homework is great. So do it. I mean, I don't know how I would scan through homework.
I feel like if people do their homework, they're going to know it better. If they choose not to do their homework, then that's their prerogative. But to make it more difficult on the whole situation at hand, then I feel like that's ridiculous. Just do what you can as far as homework goes. If you want to do the homework, then that's on you. If you don't do it, then that's on you.
Yeah, I mean, at this point, we could fax it. Does anyone have a fax machine anymore? Nice, Destiny.
Yes, actually.
Why don't you send it by certified messenger? Yes, points are associated with the homework. I do get that, Reagan. But I'm not, basically, if you can't turn it in, I won't actually count those points against you, if you get my meaning. Can we take offline and do survey?
I mean, you could always do like little tiny quizzes, asking some of the questions that are part of homework so that, I mean, it's not the full homework, but they're just like little mini quizzes in between tests.
Judging by how that works in my 121 class, that would be a bad idea. Let me think about the homework thing, my little frenetic one. Can the homework be extra credit? No. Can the homework be extra credit? That's a good one. So let me think about how the homework is. I guess if we're taking pictures of labs, let me think about that, Reagan. I'll get back to you on Wednesday. All right, so I'm gonna find a way for the exam where we can like take pictures and PDF it and upload it. I'll find a way to get it timed. And the labs will take pictures of our work and PDF it and upload it. Does the final still count as 2 grades with the lowest one dropping? So far, yes. I like how I have to have like all these windows open to try to figure this out. You guys are talking as much as you do in class. I like it. Only it's like in Charlie Chaplin style here. Who's Charlie Chaplin? And he's got those.
That was good.
All right. Más preguntas? Nice. Buster Keaton. Wow. Somebody's parents loved him. All right. Seeing no hands and no faces. Hey, how come I can't erase? Come here. It should be this button to erase, right? All right. Behold the one note as I erase. Okay. And note there's always a pause after I do this. Oh, look at this! I have a cool little title up there. Look at that. Okay, so we got a chat window up. We got this going up. All right, so let's talk about. Unless there's any burning questions, shout it out. Get one last little bit of coffee here. And let's go, Leroy. All right. Intermolecular forces. Let's go into here. Let's see how well I'm doing on my pens here. Pad here. Molecular forces. These will be called IMFs for short. We've been talking a lot about the forces that actually hold atoms together. So in the case of water, H2O, we've been talking about them being held together by sharing their electrons, fulfilling their octets, and the like. But now what we're going to do is talk not about why atoms come together, but why do molecules themselves want to stick together? What makes a water molecule want to stick to another water molecule to make enough for you to drink? Why do they even like each other at all? So these intermolecular forces, these are the forces that hold, that hold one molecule to another. One molecule to another. Or why do water molecules stick together at all? Why do water molecules stick together at all? All right. So remember when we were talking about the differences between solids and liquids and gases, we said solids were really fixed next to each other. They were tightly packed. They were basically immovable, but that liquids, like water, they mostly are tightly packed. They will slip by each other. So they definitely have some sort of attraction to each other, some sort of force holding them together. And these are what we call the intermolecular forces. Now we have 1, 2 and a half, 3, 4 that we're going to talk about. And so I'm going to sort of dive right in. The first intermolecular force that we have is the so-called ion dipole. Now, as the ion dipole might imply to some of you guys, it'll involve, well, ions. By the way, these are very weak forces, and they involve ions with dipoles. Now, What is a dipole? So actually, when I ask a question, anyone can chime in. What do I mean when I say dipole?
A polar molecule?
Yes.
2 poles.
2 poles. Now, so when we do this, I want us to think dipole means polar. Okay? Now, we've sort of already talked about this when we do something like this. We have good old sodium as a positive and good old chloride as a negative. We talked about one of them giving up their electrons, one of them taking them. They'll become charged and they stick together. Now, I would argue that that interaction is, in some respects, strong and also very weak. It's weak because all we have to do to break it is to dump it into water and the salt will, quote, disappear. Now, check it out. Why is this occurring? Well, if you remember, good old water looking like this with its lone pairs. Is that polar or non-polar?
Polar.
Polar.
Polar. So who's the greedy one?
Oxygen.
Chlorine.
Well, yeah, chlorine's pretty greedy too, but not like this. So remember, oxygen is negative, which means those hydrogens have to be positive. Now, you can imagine that if water comes into contact with a salt crystal, those negatives right here of the oxygen and the positives of the hydrogen will actually be attracted to their opposite one in the salt crystal, meaning that the negative is going to go toward the sodium and the positive is going to go to the chlorine. Now, as we do that, we'll notice that something happens. Now, when these atoms give and take their electrons, okay, they become charged. And if you guys remember, I was handing, I think it was the cloth to Jade, and I was like, look, they have to physically transfer those electrons to the other atom, at which point they're immediately charged and they immediately look at each other in a new light and stick together because of these charges. Charged particles cannot exist by themselves. They always have to be accompanied. So when this water decides to interact with this sodium and chloride, the sodium and the chloride don't necessarily want to leave each other unless they can be satisfied. Now, the delta minus and delta plus of the water are not true negatives and they're not true positives, but they are slight negatives and slight positives. So if this water is going to take these two ions and pull them apart and make them happy, they're going to have a bunch of them. So I oftentimes will like this to some sort of breakup situation where you just broke up with your significant other, you're really sad, you get like one friend to call you up and say like, hey, you can't be down in the dumps, let's go out. And you're like, no. Well, what's the easiest way to make sure that you go out? You don't get one friend, but you get a whole bunch of friends to take you out and get your mind off of it. And that's exactly what these water molecules do. So what'll end up happening is that the sodium with its plus will have the water molecules surrounding it. And what they'll do is they'll surround it in such a way as to maximize the interaction of the oxygens, those delta minuses, with the sodium. I'm going to stick another one in here. So we can see that they have those delta minuses trying to keep that sodium happy. Likewise, the chlorine is going to have similar, only this time, it's not going to be the oxygens, but it's going to be the hydrogens. And what they're going to do here is surround this chlorine. I'm going to have to stick one out here. That's okay. With their little delta pluses, trying to keep that chlorine happy. Now, what I've just drawn here is something called a solvent cage. And what that means is that the water molecules are surrounding those ions, and there are going to be a bunch of them surrounding it, such that their slight negatives and slight positives make up the difference from being separated from a true negative or a true positive.
This is not going to work.
That's not going to work? Was that a question for me, or was that? Okay, I'm going to assume that we're okay. Can somebody type something in the chat to make sure that we're all live? Okay, good. I'm just making sure. It's so weird. It's one thing to be radio silence in a room where I can look out and make sure you guys are still alive. It's another to be like complete dead air and wondering if my internet connection took a dump. Okay, so why do I call this a weak intermolecular force? Well, we actually already intuitively know that if we want to get the salt back, all we have to do is evaporate the water, and they all come back together. So pulling these things apart and sticking them back together is actually very easy. You don't have to do anything massively hard on them. Now, the next intermolecular force, this one's going to be interesting and fun, and that is going to be the dipole-dipole interaction. So dipole, dipole. Now, these guys are strong. Now, as the name implies, dipole means?
Two polar.
Polars, right? So we got a polar plus polar. So every time you see a dipole, you want to think, is it polar or not? Okay, so let's go back to our favorite little guy here, water. And this is where my big diorama is going to come in, and I'm going to make a big picture out of stuff. Brian, nice comment there. All right, so let's take a look at water, H2O. Again, we have the minus and we have the plus side of the water molecule. If I were to bring another water molecule in close proximity to this, how do you think it might want to interact?
Hydrogens with the oxygen.
And vice versa, right? So one might think, oops, let's get another picture or color there. Let's go back to our blue. One could imagine that, say, a water molecule might come in like this, where the negatives and the positives would match up. Now, in this respect, when we look at this, what we're seeing is a maximization of their interactions. Keep in mind, water molecules are not locked into a thing, just like we said that electrons are not static. These pictures that I'm about to draw are not static. Temperatures, the average kinetic energy of the molecules of the system, this is the movement energy that is going on. So these are constantly moving in and out. So if for some reason they have an unfavorable, they will quickly switch to go to a favorable. If that has a chain reaction throughout this solution, which it will be in constant flux. So what I'm going to do now is I'm going to try to get rid of that. There we go. I'm going to try to draw organically a bunch of water molecules together. I'm going to do my best to not make them look like static, perfect pictures. So I can imagine water molecules coming in like this, trying to maximize their interactions with each other. hopefully I'm making this look slightly organic here. Apologize for the dead air. It's so weird. I feel like I have to fill this like a radio station. And let me just draw another one out here so I can start building off of this. So let me zoom out a little bit there.
A lot, or is there any rhyme or reason to how many you're building? Or are you just showing us a lot of molecules?
I'm just showing a bunch of them. Because what I'm trying to do here, Reagan, is I'm trying to just make a smattering of these things, and they shouldn't look like they're. So what I'm trying to avoid is drawing the molecules all lining up where you have your negatives, your negatives and your positives all, lining up all perfectly. Because they are constantly in motion, because they're constantly moving around, I'm hoping that we see sometimes unfavorable interactions. So what do I mean by that? Clearly, right here, I have a delta minus and a delta plus hanging out next to each other. That's good. But right here, I can see that very temporarily, two hydrogens are next to each other, which they wouldn't want to because there's two pluses close to each other. Well, right now, that O and H interaction is overriding that. But in the blink of an eye, all these things could move, and those two hydrogens could push each other away and reconfigure. And so what I'm trying to do by this organic picture is to show you that nothing is static, and all they're trying to do is to try to maximize those minus and plus interactions. And they will constantly be moving, and that's okay. Now, you can imagine that these are actually pretty strong interactions because we actually have some sort of just a myriad delta pluses and delta minuses interacting in such a way to make a cohesive net here. Now, what I want to do next is add in some ammonia. Oh, I gotta zoom in for that, sorry. Make that look a lot better. So NH3, ammonia. We've drawn this plenty of times. Okay. Now, is ammonia polar or non-polar?
Polar.
Polar.
So who is the greedy one?
Nitrogen.
I mean, nitrogen.
Nitrogen, that's right. So that's negative and that is positive. Remember that NH bond was one of the ones you needed to know. So if I dump ammonia into this water, will it want to mix with the water? Pro tip, the answer is yes.
Yes.
And we know that physically because we all have Windex somewhere around our house to clean glassware. And that is a dilute ammonia solution. And so we do know that ammonia will mix with water. So what I'm going to do is I'm going to dump this ammonia into the mix and sort of see how those two might interact. So, oops, I might dump in an ammonia and it might take us 3 feet out. I'm going to zoom in here to make it a little bit the same scale. Oh man, this is going to be fun changing my pen colors here. It's a little easier when I'm physically there. I think my kid is singing, "We Built This City on Rock and Roll." That's his new jam right now. So if I keep building this, and I will zoom out and pause here in a little bit to let you guys catch up if you're writing some notes. And you don't have to draw exactly what I have, Reagan. just sort of, once you get the idea here, you can try to draw your own. All we're doing is maximizing the nitrogens to hydrogens and the oxygens to hydrogens without sort of locking them into place. So I'm going to try to get this going on here. So I'll even draw another ammonia onto another ammonia here. And then maybe another NH3. And let's see what that looks like now. Oh, we should get up here and get some up here. So all I'm doing here is trying to maximize some interactions, but not make them perfect. Once again, I'm trying to show the delta minuses to the delta pluses, the delta minuses to the delta pluses of these guys getting together. So once again, these dipoles want to interact. They'll constantly swim around and maximize delta minus and delta plus. Okay. Let's add one more in here. Let's do CH3, CH2, OH, AKA alcohol. Now, do alcohol and water mix?
No.
Yes.
Yes.
Who said no?
Nathan.
Yes.
Nathan, are you old enough and inclined enough to imbibe the drink?
I have an Angry Orchard nearby.
So we do know that alcohol and water mix, and we know that because, you know, beer is 5% alcohol. What's the rest of it? Water. So whether it's normal alcohol or if it's your isopropyl alcohol, the other thing that is in there is water. So these two things very much like to mix. Now I'm going to go ahead and abbreviate this guy to look something like a CC to an OH. Actually, let me be a little clearer on that. I'm going to do OH like this because we all know that oxygen, when it's in the middle, is going to bend something. Okay? So what can you tell me about this part right here, this CC stuff with the implied H's, all this CH stuff? What do we know about that? Is it polar or non-polar?
Polar.
It is actually non-polar. That part is non-polar because remember the CH bond is non-polar. So this guy right here is non-polar. But what do we know about this OH bond?
Polar.
Yeah, absolutely polar. So what we have here is the mixture of something that has polar and non-polar aspects to it. Now, it is such a small molecule overall that the polar aspect will mostly dominate the properties of this molecule. As long as you have a 4-to-1 ratio of carbons to oxygens, you will be polar because those oxygens being so greedy will make a polar overall somewhere. If the chain gets too long, you know, if you get like 20 carbons and only 1 oxygen, then that whole CH non-polarity will dominate. Sometimes I liken this to thinking about trains. I mean, right now that's all my kid's thinking about is making trains. If the train is short enough, you're able to see the engine, the driving force of that train. But if the train is too long and you just happen to take a glance at a train, you might only see the boxcars, the non-polar part. So if you have too many boxcars to engines, it'll be non-polar, but if it's a small enough train, you will always be able to see the polar aspect. So knowing though that we now have a polar part here, right? We got this polar aspect right here. What I want us to do is now dump these guys into the mix as well with the ammonia and the water. Like dissolves like, so if they're all polar, they will all want to mix. So I'm gonna have red for the alcohol, purple for the ammonia, and let's get some blue water. Oh, and let's put my glasses on. What? Oh, man, that's nice. Hey, why don't we go ahead and fix this guy while we're at it? Okay, so I'm going to go ahead and dump in my alcohol here. And maybe make it still interact with some ammonias, nitrogen. And some waters. And I'm just going to keep randomly putting these guys here somewhere. And if you guys go back in your lab, you'll see why I'm drawing the alcohol molecule like this, because you did do it in the lab. It was a C to a C with an OH bent. So I'm going to go ahead and continue that line of drawing. Normally, if we were in class, this is the part where people would just start taking pictures and then redrawing their notes a little bit later. So it's okay if you're feeling a little overwhelmed with this gigantic thing that I'm drawing here.
Is this drawing going to be in the PDF?
Oh yeah.
Okay.
The end product though is what you're going to see. So you won't see the progression, and that's why I said you might want to maybe look at this in conjunction with the PDF, because what it will allow you to do is to see why I was doing what I'm doing here. So I'm going to, and I'm actually going to do this. Let's get another ammonia in here. Kind of sucks because like my board writing is so much better than my handwriting. Of course, some would argue that it doesn't matter because all my writing sucks. But I'm working on it, guys. I'm working on it. Okay. I think I have enough in there. And once again, I just want to point out that I'm trying to get these delta minuses to the delta pluses of all these guys. Delta minus to the delta pluses. Okay. Questions so far?
Nope.
No, we're all right. Okay. Man, I didn't realize I was so badass at online instruction. This is good. All right. I do want to point out one thing that might be a little lost here. I'm going to go ahead and circle it in black here.
It's a little confusing for me.
Well, then why don't you speak up and say I have a thing. What's wrong? What's wrong, Sume?
I get lost when you start mixing the ammoniac and the water about the delta and minus and delta plus.
Yeah.
And after you add the alcohol. So now I'm looking and I can't find the polarity of the mix.
What do you mean you can't find the polarity of the mix?
So now I don't know. I try to follow with you. I don't know if now when you mix alcohol and ammonia, if it's polar and non-polar.
So yeah, so I think I see what your question is. when you look at the fact that alcohol has some non-polar aspects, but it does have a very polar OH bond, right now that OH bond, because the molecule is small enough, will dominate the properties of this molecule. So it will mix with other polar things. Now you may ask yourself, okay, so what's going on with that little CC stuff that I circled in black, or what's going on in the other one in black that I circled here with the carbons next to the hydrogen of water? Well, let's start with the little CCs that I have over here on the right. Remember, those two are non-polar, okay? And I just said that like dissolves like, or birds of a feather flock together, whatever idiomatic expression you want to use. If polar things want to go together, then non-polar things would like to get together. So that's why I drew those two alcohol molecules where the carbon chains happen to buddy up there. In the other black circle, you notice that I have the carbon chains interacting with that hydrogen, or even dare say that oxygen, and you say, but that wouldn't want to happen because that's non-polar and those things are polar. And you're right, they wouldn't want to, but they're forced to because the OH bond at the end of the molecule says, whether you like it or not, we're going to go into solution. You're going to be uncomfortable. That's okay. We're going to keep moving, and you'll get used to it, is essentially what that OH bond is saying to that unfavorable interaction. Basically, they're saying, I'm going to dominate the intermolecular forces here. I'm going to tell you what to do, and we're going to go swimming. I'm sorry you're uncomfortable. Does that help a little bit, Sume?
Yes, thank you.
Okay. Yeah, by the way, I am going to get to the viscosity and stuff. That's at the end of everything. So, so hang tight, guys.
Okay.
Forrest, at the end of this, so you kind of wrote this willy-nilly and you said not to worry about it, and you're doing the delta plus, delta negative. If you were to do this, would those equal each other? Would the count equal each other? So you'd have 20 negative, 20 positive connections.
Both yes and no. And I'm going to hedge my bet on that, because what I'm going to say is this isn't about all positives and all negatives equaling each other, because we're not actually building a compound like we would with sodium chloride. What we are doing is building a network of forces that would hold things together. So I'm not worried about making sure I have an equal number, because at any split second, these things will move again. A sodium chloride molecule does not move, right? Once they exchange their electrons, they are locked together. If you decided to Google the structure of the salt crystal, it is this beautiful cubic lattice work that is locked in solid and never moves. So yes, in that case, the sodium chlorides would have to absolutely equal the exact number of positives to the exact number of negatives. But since we're talking about fluid situations here, there's no way to keep track of all the positives and negatives, and the minute you did, they would move anyway. So I'm only putting the positives and negatives there to just demonstrate that there's going to be a significant number of them, but I'm not worried about making sure that they are exact, because that's pointless. Does that help?
Yeah, so what you're showing us is a fluid structure so that
Yes.
the negatives don't equal out. But if something that is unchanging and or like, I guess, rigid in its structure, that those would equal each other.
Right, those would have to.
Okay.
And in fact, I mean, if you wanted, I mean, this is really what sodium chloride does, is they do, I'm just gonna go ahead and do the colors. I'm not gonna worry about writing it. So you'd have a sodium and a chloride. And this is how they build up. They just lock themselves in to this beautiful little lattice work, and they have to equal each other. The fluids do not. Let's see, do I have green here? One of the important to note under the dipole-dipole is there's something called the hydrogen bond. Note, not a bond. It is a misnomer, but the hydrogen bond is really a subset of these dipole-dipole interactions. So I put it here in green under the dipole-dipole. It is a subset of dipole-dipole. Subset of dipole-dipole that must have see where I'm at in my thing. Do I have enough room to go over? Yeah, it must have nitrogen, oxygen, or fluorine with a hydrogen attached. Okay, it should be noted that these are stupid strong. These are stupid strong. Now, let's set the Wayback Machine. We talked about oxygen and hydrogen getting together. We talked about them sharing their electrons to fulfill the octet. And then we talked about them not sharing equally, okay? We said the oxygen is actually really greedy and will now hoard those electrons, creating that dipole. Here's where it gets fun. Every now and again, you can imagine that if I were to look at a water molecule, and we have this HOH with its lone pairs, and we see an H to an O to another H with its lone pairs. You remember that coordinate covalent bond where one atom donates the entire lone pair to make someone happy? Well, take a look. I've got an entire lone pair. I will totally give it to you if you want it. And that hydrogen is very tempted. Now, is that oxygen here on the right going to allow that hydrogen to leave?
No.
No.
No, of course not. If it did, it would lose its octet. But here's the funny thing. Every so often, this does work. Every so often, an oxygen, oops, really entices someone else's hydrogen. Oh man, that is horrible handwriting. Let me try that again. Now, it entices. Okay, the hydrogen bond, we'll talk about it later on in this class, actually physically stealing it. Right now, this entices it, and it's really making a case for, like, if I just give you the two, will you come with me? The oxygen on the right says, hang on a minute, buddy, that's not cool. But let me ask you this. What if I had another water molecule down here? Don't you think that that guy could be doing the same thing to another water molecule? Essentially, this reminds me of a bad like love triangle or something going on here, where everyone is trying to steal someone else's partner here, and it just isn't going to work because you're never going to leave that person. What it does is make a tangled web of incredibly strong intermolecular forces where everyone is tugging on everyone else, but never quite pulling it away. Okay? Everyone is offering the lone pair to everyone else's little hydrogen, trying to take it, and that hydrogen is very tempted, but will never leave the one they're with. And so the reason why this is called a hydrogen bond is because if we can imagine, and I'm going to go ahead and draw these in here, I'm going to zoom in here. What we're going to see, let me get a bigger thing here, is that every single one of these oxygens or nitrogens or fluorines is going to be enticing someone else's hydrogen and sort of saying, hey, why don't you come with me? Now, as I zoom in, those just look like little dotted lines. And that is to say that it is not a true bond, but rather just another sort of intermolecular force, an attractive force between those hydrogens and those nitrogens or those oxygens. And the reason why it gets that misnomer for the name bond is because as I zoom out, if we squinted, it would almost look like those are bonds. And that's where it sort of gets that misnomer of being called a bond. It's not a bond, it's just a stupid strong intermolecular force where these very electronegative nitrogen, oxygens, and fluorines are trying to pull a hydrogen off of someone else who is not going to get rid of it. Now, this is where it becomes very important here. So normally I just go to a periodic table and show you this, but I'm gonna do a little special note here. Special note. Why are these H bonds, hydrogen bonds, so special? Okay. The hydrogen bond is kind of interesting. If we think about intermolecular forces in general, so let me just say this, IMFs in general. The bigger you are, the stronger your intermolecular forces. The bigger you are, the stronger your IMFs. Now, how do we sort of know that intuitively? Take a look at the periodic table. I don't happen to have one, but hopefully someone out there has one and can take a look. Or if you recall, let's look at the look at the halogens. Okay. Of course, they're all diatomic. We have fluorine, chlorine, bromine, and iodine. You'll notice that I decided to color code them. Why did I color code them? What do we know about their physical characteristics?
Solid, liquid, or gas?
Yeah. So we take a look at that fluorine and what does it say? They're weaker than covalent bonds, but they're less stronger than, what is this? So someone at Mustard Man over on chat real quick said, aren't H bonds weak since they are temporary? Insofar, yes, they're weaker, but what they do is because there's so many of them and they're locked on top of dipole-dipoles, they actually have a much greater overall strength than any of the other intermolecular forces. So Actually, and it's not that they're weak, it's just that they're on small molecules. Take a look at this, Mustard Man, and maybe this will sort of demonstrate why they're so important. As was noted here, we did the solid liquid gas thing here. These guys here, these are gases. The bromine is a liquid, and the iodine is a solid. The reason why iodine is a solid is because it is so much more massive than fluorine, chlorine, or bromine. And so as those guys decide to get together, they can influence each other and otherwise cause there to be much stronger interaction. That's why they're a solid instead of a gas running around freely. So, and of course, normally I would say this. You guys all remember Sume. If I walk into a room and Sume walks into a room, who do you think you're going to listen to if they tell you to jump? Me or Sume?
Sume.
Yeah, he's a big guy. You don't hire bouncers that are small people, right? Sume would be our bouncer. He wouldn't have to say anything. He would just be like, "Hi, let me check your ID." No one's going to mess with him. If I'm the bouncer, people are going to mess with me left and right. I do not have that charisma, that intermolecular force between me and other people to say, you should listen to me. Iodine is bigger than fluorine. When iodines get together, they say, we're just going to sit this one out and stay a solid because they can influence each other and make that strong intermolecular force. Now, why is H bond so special? I just talked about the size. The bigger you are, the stronger you're in IMF. So the curious aspect of this is the following. Oops, whoa. Oh, sorry, you were big. Let me get back over there. So if we look at this, here's something that is curious. I have H2O, H2S, and H2SE. Now, H2S is hydrogen sulfide gas. It smells like rotten eggs. It sucks. You really don't want to breathe this. H2SE is also a gas, a very deadly toxic one. But we all know that water here is a liquid. Now, if you look at the periodic table, sulfur and selenium are much more massive than oxygen, which means that those molecules themselves are also much more massive than a water molecule. So if they're gases, that would imply that water should also be a gas because it is so small, it shouldn't have enough intermolecular forces between them to actually coalesce and become a liquid. But they do. And they do that because unlike sulfur, unlike selenium, those guys can't really make those hydrogen bonds, but water can. And it's that extra stupid strong intermolecular force that allows them to be attracted to each other, to coalesce and become a liquid. Remember I said these intermolecular forces, these dipoles, these are really, really important. If hydrogen bonds did not exist, we wouldn't have liquid water and we wouldn't be there. Keep in mind, both molecules have to have nitrogens, oxygens, or fluorines, and each of them must have hydrogens as well. So if the other one does not have another hydrogen to play, then this wouldn't happen. So if you had, say, water and, I don't know, sulfur dioxide, while sulfur dioxide is polar, it does not have hydrogens. So it therefore could not hydrogen bond. Mustard Man, did that maybe answer your question? Cool. All right. All right. So we can have ions and dipoles, great. We can have dipoles and dipoles, cool. Hydrogen bond subset. Let's talk about what happens when you have a dipole with an induced dipole. So here I want dipole, induced dipole. All right, April, I think you've been the one answering this. Dipole, what does that imply?
Polar.
Polar. So then what would induced imply to you?
Forcing it.
Forcing it. So where have we all heard the term induced before?
Labor.
Induced labor.
Labor. Everyone always goes to labor. Yeah, and what does it mean to induce labor? The kid doesn't want to come out, but it's time for the kid to come out, so they make it happen. So we already said that dipole is a polar molecule. So if we're going to force something to have a dipole, it means instead it must have been nonpolar to begin with. So the induced dipole is a nonpolar molecule that we are going to make become polar. So I'm gonna, oops, whoa, hey, get back here, there we go. So I'm gonna put one out here that we have all seen and loved. Good old CO2 with H2O. If I draw CO2, oops. If I draw CO2, which we've done like countless times, and we know that the CO bond is polar, we know that we've got like a delta minus on both of these, but again, that tiny little delta plus is hidden. Let's say that my water molecule does interact with this, and we know that water and CO2 does interact. How do we know that those two interact? We have a physical example in real life. Man, if only I had myself a soda right now, it'd be so awesome. What happens when we crack open a soda?
CO2 gas is released.
Yeah, that's that that we hear when we open it up. So we do know that carbon dioxide and water will mix. Beer, as Vince says as well, yes, those are carbonated drinks. So some CO2 will dissolve in water. Not a lot, but some. Because we all know that if we leave our soda out for too long, it eventually goes flat. We'll talk about that in a second. If I'm a water molecule, okay, if I'm a water molecule coming in, one can imagine that I come in with my delta plus facing that delta minus of, oops, what am I doing there? The delta minus of the CO2. Now, at this point, you can sort of think about this as the oxygen has got that negative, the hydrogen has the positive. All those electrons that are sitting around that carbon dioxide will suddenly like go like, ooh, what is that? Is that a positive? And they will start rushing over to that oxygen on the right because they're excited to see another positive charge there and they want to interact with it. What that's going to do is very temporarily make that carbon dioxide look like the electrons have sort of whooshed to one side. Now, they'll never violate the octet, but they will start to crowd around one side of that molecule. That crowding around will cause one side to be slightly negative and the other one to be slightly positive. And there will be some sort of interaction between water and CO2. However, as fast as those electrons are rushing over to the right, the carbon is like, hey, what are you guys doing? You guys get back where you belong. And they're like, but carbon, look, there's a big positive thing. And carbon will look over and say, really? Because I see like this. Now, why did the water molecule suddenly flip? The answer is why not? Everything is in motion. And of course, as soon as the carbon points out that it's not a nice and bright, shiny hydrogen, but it's actually a big, scary O negative, right? O with the delta negative, everyone's going to freak out and rush back the other way. And what this does is it creates a very temporary, very weak induced dipole. So let me just go ahead and put that back here. Oh, I wanted the H's over there, sorry. Okay. So what this does is a polar molecule will make a nonpolar molecule have a very weak, very temporary dipole. This is going to induce that dipole. Now, it doesn't want that dipole. And so as fast as it made it, it's going to unmake it because it didn't want that to occur. And of course, as fast as that carbon said, hey, what are you talking about? It looks over to the other side. A water molecule has decided to move on or flip itself or otherwise not remain static. And those electrons race back to the other side. And the carbon's like, why are you freaking out? And basically, all of those oxygens on the end are constantly being spooked, either for or against, interacting with that water molecule based upon that sort of movement of those electrons as they hoard from one side to the other. But it is to be noted here that these are very temporary, very weak. So let me do that. Wow, I need glasses all the time now. All right. So again, and I'll answer that question here in just a second. Destiny. Very temporary, very weak. Now, Destiny says, will they hydrogen bond to each other? They will not. Remember, it has to be nitrogen, oxygen, or fluorine with a hydrogen. And while the water molecule has that, the carbon dioxide does not. Yes, there's an oxygen, but there's no hydrogen with it to do the exchange. To say, okay, I'll tug on your hydrogen if you tug on mine. Does that make sense?
Yes.
Perfect. Now, again, physically, we know that these are very temporary, very weak interactions because, as we just said, we'll crack open that can of soda, we'll crack open that beer, but we better finish it in a reasonable amount of time or it's going to go flat, right? And what does it mean to go flat? All that CO2 has left the building because there's only so much that water can induce on a carbon dioxide molecule. It's nonpolar. It doesn't want to be there. It'd rather be a gas and fly out. So there's only so much that the water can hold. Now, it should be noted that the more carbon dioxide you put there, of course, obviously, the more you could make the water interact and the more you could make dissolve into the water. That's why we have that sort of when we open it up. That is because sodas, beers, etc., these are all packed under pressure. They inject a whole bunch of carbon dioxide in there. They pressurize it on top with a lot of carbon dioxide to say, look, I know you don't want to be in there, but I am going to put you in there and you will interact. As soon as I release that pressure, then the carbon dioxide says, great, now I have a way to escape, and they try to bubble out. There's always going to be some. In fact, I just did this last night. I got up to change a diaper at like 2 or 3 in the morning. I was thirsty. I grabbed a glass from my cabinet. I got some water. I didn't finish it, and I sat my glass down on the countertop. This morning, I came in and noticed that there were little gas bubbles on the side of my glass. That was the excess carbon dioxide when I opened up the spigot and I mixed with that little aerator, trapping that carbon dioxide in as it mixed. When I just left it alone and let it sit all night, they decided to come out and form bubbles on the inside of my glass. There's a finite amount that will stay in there, but some will. And this is one of the reasons why oceanographer people, they're really worried about CO2 emissions, because the more CO2 we have in our atmosphere, the more that's sitting over the top of our oceans, the more our oceans can be forced to absorb. Now, when you take CO2 and water, you actually make carbonic acid. It's a weak acid, but it exists. And they're not talking about actually turning the oceans into acid. What they are doing is talking about changing the pH of the oceans and making it slightly more acidic, which could really make a bad day for most marine life. Okay, I think I got everybody there. Let's go to the last intermolecular force that we have, and that is going to be the induced dipole situation. So here we have, we have induced dipole, induced dipole. These actually have a more formal name. These are called dispersion forces or London forces, sometimes also called London dispersion forces. And technically every molecule has this no matter what. The big thing about these guys though is it should be noted, these are extremely temporary and extremely weak. And why is that? Well, if we're talking about an induced dipole situation, are we talking about polar molecules or nonpolar?
Nonpolar.
Non-polar.
Polar. So this is a nonpolar plus a non-polar molecule. So you can imagine that it's one thing to say, look, I have water here. Water has a dipole. Water has a plus. Water has a minus. I can influence some sort of nonpolar molecule. Well, how is it then that two nonpolars would even want to do this in the first place? We know they will. Oh, hold on. We know they will. See if I can just move that. Hey, come here. And then I need to just like move it over. Oh, look at that. We know they will because oil and water don't mix. Remember when we had that demo of the cylinder, I said they won't mix. We all know this. Now we're going to know why. If polar things like to dissolve with polar things, and you can sometimes get that water to do a CO2, why is it that oil and water won't mix? Well, it's because oil is a non-polar molecule, okay? It's not polar, and it's a really big molecule, so for water to try to exert itself is kind of, it's kind of like boxing a glacier. You just can't do it. It's too small to take something big like an oil molecule, which is like 20, 30, 40 carbons long, and say, hey, I want you to be polar for just a second. And the oil molecule says, slough off. I'm not doing that. And therefore, they will not mix because there's no driving force to get the water and the oil to want to mix. But for a few of you out there, you do know that oil and gasoline mix. And those are both nonpolar molecules. Water doesn't like gasoline, water doesn't like oil, but oil and gasoline do mix. So how does this work? Well, first, let me note that it's nonpolar, and that these are extremely extremely temporary, and extremely weak. Right here you have two nonpolars trying to force themselves upon each other to interact. What I'm going to do here is draw, say, a hexane molecule. And a hexane molecule is just 6 carbons long. And I'm going to go ahead and put all the hydrogens on it. We're going to fulfill some octets here. So for anyone who has taken a bio class, you may note that they often leave the hydrogens off. Clearly, this is a messy drawing. And I have drawn it in a seesaw fashion because if you remember back to your lab, if you chained a bunch of carbons together, they would actually make this zigzag formation. I'm going to go ahead and simplify this to look like this. Every point is a carbon. And hydrogens are implied. It's just a simpler way of drawing these molecules. Now, what I want to do next is say what makes these two things come together. Why would they come together? You can imagine, hopefully, that as I get these two molecules closer and closer together, okay, if I get them closer and closer together, and I'm going to very falsely show them really lining up, will their hydrogens over here start to see each other?
Yes.
Yeah, absolutely. You know, if you're in a crowded room, eventually you're going to feel those other atoms, those other people close to you. Well, if you think about it, they have a bunch of electrons in and around them that are making those octets, that are trying to keep those bonds together. That means their electrons get to see each other, right? So as they get closer, their electrons now start to see each other. As the molecules get close to one another, their electrons will see each other. Well, if they see each other, what do you think they want to do? Do they want to hang out?
No.
No, because electrons are negatively charged. So guess what? They scare each other. The electrons will see each other. They will scare each other. Oops. They will scare each other. Run away. Create a very temporary, wow, what is wrong with my handwriting? Still learning to write with this thing. Create a very temporary dipole. I'm not even going to assign a delta plus and minus to it because it is pointless, because as fast as they do that, those carbons in the middle are saying, what are you doing? Get back to the other side, and they're like, no, scary electrons. They'll be like, where? Now, what will end up happening with these larger molecules is it eventually when you get a bunch of them next to each other, when they start scaring each other, when they start moving and creating these temporary dipoles, they'll eventually start to sync up. Now, if we were in a physical classroom, I would normally ask a bunch of volunteers to come to the front. Typically, I would ask about 5 or 6 guys to come up and join me. We would get to the front of the room. Do you think we'd stand all right next to each other? Or would we space out across the front?
Space out.
Yeah, we absolutely would space out. There would be no reason for us to decide to get all up there and huddle in and sing Kumbaya. We have no reason to want to interact. We all look the same. Oftentimes when I bring the people up, we'll stand with our hands in our pockets or behind our back or otherwise minimizing all interaction. Now, at this point, I would normally get everyone to start moving in closer and moving in closer until we were like sandwiched next to each other like sardines. Well, at that point, someone's going to get uncomfortable and they may start fidgeting. Now, their fidgeting is going to cause the person next to them to fidget likewise, and so on and so on. And eventually, we would find that all of us started fidgeting exactly the same way. We were influencing each other to move in exactly the same way. And that's what these electrons start to do, is they start to essentially sync up, inducing dipoles upon one another, and therefore make a very slight, very temporary, very weak, extremely, but enough to hold them together. Now, here's the fun part. If they're so weak, then why would they be able to stick together, like, say, in the case of oil? Well, they're very weak in a one-on-one situation, okay? If I were to compare an induced dipole to a dipole, there's no competition. The dipole wins for strength. The thing is, and again, let's come back to it. Look how big a water molecule is. Hexane is already a lot bigger. And most of these induced dipole interactions involve very large molecules. And so while they might have individually extremely weak bonds, their trick is they're rolling 100 deep. And so normally at this point, I would maybe have a volunteer and I would make a nice little hydrogen bond with a person, and it would be a big strong handshake, and they could hold on to me, and I'm not going anywhere. And then I would make an induced dipole link with someone where we just interlock pinkies. Well, I can pull away from that really quick. It's a very, very weak interaction. But reminding us that they roll 100 or so deep, I would then engage all 4 fingers with the person, and suddenly it's a very strong bond because I have just so many. It's kind of like Velcro, right? It's all easy to break one of those little Velcro loops, but to break them all at once, that's not going to happen. Velcro is not very strong, but you get enough of them, very strong. So when we talk about this relative strength, we're talking about one bond to one bond. We're not taking into account how many they're rolling in with. Does that make sense? Well, I wonder how many people are still participating.
Yes.
Yes.
Okay,
Yes.
well, I was going to try to look at the participant list, but
Can you
people
explain that
are-
one more time, please?
Emily's like, kinda. Which part?
The one, the last thing you just said.
So if we were to look at, say, water versus oil, okay, and we'll talk about this in just a second. Oil actually has overall the stronger intermolecular forces overall. And that's because if we look at, say, a cup of water versus a cup of oil, we'll find that we can say boil water before we boil the oil. We can actually cause water molecules to leave their friends before we can make oil leave their friends. And the reason is We say water has an incredibly strong intermolecular force. It does. It has dipoles, yes. It has hydrogen bonds, yes. But it's really, really small, and it's coming in with one of those bonds. An oil molecule might have 40 carbons to it, which means even though each of those individual bonds is very weak, it's bringing a lot of them. And so overall, you just get overwhelmed by all the tiny little intermolecular forces that on the whole sum up to a much larger, stronger intermolecular attraction between such big molecules. Hands up on a participation list. Jump in if they're new. If they're old, you go put them down. But by all means, unmute yourself and jump in. Emily, did that answer your question?
Yes, it's Yadira.
Oh, it's Yadira? Sorry. I just saw
Yeah.
Emily kinda. So now Emily says, yeah. Okay,
Thank
so
you.
you know, if on an exam it says which is the strongest intermolecular force, of course you want to go with the dipoles. Of course you want to go with the hydrogens. If it says what's the weakest, you would say the induced dipoles or the dispersion forces. Well, what I want to do now is I want to talk about not an individual intermolecular force, but an overall, as I was sort of saying between the water and the oil there. So what I want to look at is those physical properties. So as someone asked earlier, is he going to talk about viscosity and stuff? Here we go. So let's talk about this. I'm going to go ahead and draw a nice little line here. I want to relate these intermolecular forces to physical properties. So relate physical properties to IMFs. Okay. So I'm going to look at 4 different intermolecular forces, and I want us to just sort of think about this qualitatively. We already know the answers. Let me make that a better F. Okay, the first one I want to talk about is boiling point. And I want to ask you a question. As the intermolecular forces increase, what happens to the boiling point? Will that boiling point increase or decrease?
Increase.
Decrease?
Increase? You guys agree?
I say increase.
Yes, it absolutely would go up, right? Because what does it mean to boil something, right? What are we doing when we boil something? Never thought about that, huh? Lots of things we do in life we don't think about. Think about the phase changes. We are taking liquid to a gas. What are we doing? We're vaporizing it. We are trying to force these molecules to no longer have an attraction toward one another. Okay? We're putting in energy to try to say, look, I know you want to be next to the other water molecule, but I'm not going to let you. So if something has a very strong intermolecular force, it is not going to want to leave its buddy. You're going to have to put more and more and more energy into that to finally say, look, I told you, go away. So as the intermolecular forces go up, absolutely the boiling point will have to increase. Stronger IMFs.
We have some background noise. Some people have the mic on. Can you tell them to turn off, please?
Whoever still has their mic on, go ahead and mute it. Stronger IMFs mean it takes more energy to make them. I don't want to go too far out to a side. It takes more energy to make them leave one another. Okay, the next one I want to talk about is viscosity. All right, viscosity. Ooh, what is viscosity?
A liquid's resistant to flow.
Wow, someone says a liquid's resistance to flow. Very nice on the formal definition there. And that's totally fine. Most people think about viscosity as the thickness of something. And for the most part, you could probably rely on that until you get into some other situations. But you are right. Viscosity is the resistance to flow. So what I mean by that is if I take a glass of water and I dump it out on the countertop, we know that that is going to flow right out of the glass and spill everywhere. But if I take a glass full of honey, it's going to take a little longer because of those honey molecules flowing past one another. Go back to the idea of it being a liquid. They are mostly tightly packed, which means they do move and slip past one another. Think about washing your hands, right? They have to move and slip. The stronger your intermolecular forces, the less you want to flow. So as the intermolecular forces increase, the viscosity also wants to increase. You want to resist more and more. So stronger, zoom in so I don't lose my handwriting here. Stronger the IMFs, the less you want to move. Read, love. What? Now we have surface tension. Surface tension. Okay. Pro tip, what is surface tension? This is funny. Surface tension is a fancy way of saying the tension at the surface. Sometimes we're not very imaginative in our descriptors. So the surface tension is the tension at the surface. And we all know and love this situation. Is there a question? We all know and love this here. Let's see.
Someone has their mic on. Can you please turn it off?
Oh, I needed to make that a little bit of a body here. Let's make a body. There we go. Let's get some legs out here. There's like a nice little pool of water, and I got a little bug on that. Anybody recognize that? With my horrible drawing?
Is that an ant?
Is it an ant? Actually, yes, it could be an ant as well. I'm more thinking that this guy right here, this is one of those water striders or water skeeters or water skitters, or however you are, where you're from, you know what I'm talking about. Those bugs that can walk on water, right?
Yeah, they're awful.
Why are they allowed to walk on water?
Okay.
Is it an ant? Ants will do this too, by the way. Ants can also do this. But how is it able to sit on top of the water?
Because they're light enough?
Well,
They have a
yes,
different
it has
kind
to do
of-
a little bit with their width or their weight. April says the tension. Keep in mind, you and I try to walk on water. That's not going to happen, right? That's because we weigh a lot. And the force that we are pushing down on the water is enough to break the tension that each of those water molecules have. These guys don't have enough weight, not to mention they also have tiny little fingers off the bottom of their feet that are spreading out that weight over a great big area. They don't have enough force to actually tell water molecules, move aside. Okay? They can't do that. The other place you may or may not have seen this, stop me if you've seen this before. But if I have a penny and I were to drop a bunch of water on there, eventually it would do something like this. Has anyone ever done that before?
Yes.
Yeah. And if you haven't done that, you've definitely done one of these. It's Mother's Day. You want to be very nice. You decide to bring mommy a hot cup of coffee and you want to give her a whole bunch and you fill it all the way to the top. And it's like brimming over the edge. And you're like, oh dear. Yeah, we've all done that. Why is it not coming off the penny? Because those water molecules just don't want to let go of one another and flow. So this surface tension, the tension at the surface, is all about those guys hanging on to each other. So one can imagine that the stronger the IMFs, the stronger they hold on to each other. So this means that as the IMFs get bigger, the surface tension also increases. I guess since we're making, I guess I might as well say surface tension, right? Okay. The last one here that I want to talk about is vapor pressure. Now, I won't bore you with the details of this. This happens to be the pressure of a vapor above its liquid. Now, it's important that we say that it's above its liquid. You have to have that liquid in order to get that vapor in the first place. If anyone's from well, technically, we're from a wet climate. We have the bay sitting right there. We have the Napa River sitting right there. We have a lot of water nearby. We constantly run at 50% humidity, sometimes more. But I'm from Bakersfield. There ain't water around there. It is a very dry environment because there's no water around to put itself into the atmosphere. So this is kind of interesting. The more it can put itself into the atmosphere, the greater its pressure will be. So the more it can put into the atmosphere, the greater the pressure. And although it's not the best of analogy, if you've ever been to a humid place, say the Caribbean or Hawaii or the South or the Philippines or something, you know you're in those places because you step out the door and it's incredibly humid and it sort of feels very muggy and pressury. That's because there's a lot of liquid out there and they're exerting their pressure because they've been able to get there from the surrounding waters. Now, this is where it gets interesting. I want to ask, as the IMFs get bigger, what happens to the vapor pressure? What happens to the amount of stuff you can put in the atmosphere? Does it go up or down?
Decrease.
It will go down, right? This liquid is trying to put itself into the vapor. Well, if its buddies are holding on to it, like we see up here in the water, if they are hanging on, it won't be able to go into the atmosphere. So the stronger the intermolecular force is, the amount of vapor you can put actually goes down. It's the only one that's backward. It actually goes down. Okay, so now I kind of want to play a game. I want to play a game of who has the stronger IMFs and why. I want us to think about this not in terms of necessarily right now, dipole, and whatever, because I'm going to put stuff up there that you have no idea, but you do know the answer. So I'm going to put up a couple of pairs here, and you're going to ask me why. So I'm going to put up the pairs, and you tell me why that one wins. So let's go with H2O versus alcohol. Which one of these has the stronger intermolecular force? April says water.
Water.
Water, okay. So June, you typed in water. Why does water physically have stronger IMFs? And I don't want to hear dipole, or hydrogen bonds because alcohol has all those too. Why is water stronger? June?
Because they like to stick together.
They do. The boiling point, that's a good one. Vince says a higher boiling point. So why? Higher boiling point. You may also have said it has a lower vapor pressure because you'll smell the alcohol before you would smell water. Someone says water because it will not evaporate by itself. It will, but not as fast as alcohol. So there's your vapor pressure. What about the following here? I'm going to do pancake batter versus water. All right. Someone says batter. Oh, someone said water. Okay. Brenda, why did you say water?
Because of its
Because of the viscosity? Okay, have you made pancake batter? You will pretty soon in this lockdown. Yeah, the pancake batter is going to be because of the viscosity. If you've ever made it, it gets really thick real fast, right? And it resists you trying to stir it. So, let me go this. We have pancake batter. Oops, oh shoot, undo. We'll have pancake batter because viscosity. Okay. What about, water versus oil.
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 Oil because?
Viscosity.
Right, so we have viscosity. You might also say the boiling point, as I mentioned before. Water will boil and oil will not. That's the reason why we fry our food. That whole like bubbling, by the way, guys, I don't know if you knew this. that bubbling is all of that water inside of your vegetables and stuff boiling off because that oil was so hot. That's the crackling you're hearing and seeing when it's frying. You're not doing anything to the vegetables just yet. You're getting rid of all the water. Technically, for all my chefs out there, that's why frying is dry cooking. You're getting rid of the water, just like in baking. Let's see, viscosity, what is another one? Oh, what about gas versus oil? What do you guys think?
Oil?
Ooh, we got somebody saying gas, somebody saying oil. We got some question marks. All right. Vince says oil because of viscosity. Vince, give me another reason why. What do you mean? If I spill oil on the ground and I spill gas on the ground, which are we going to smell first?
Gas.
Yeah, right. That thing is going to vaporize very quickly. So viscosity and also vapor pressure.
Also
You're
because
not
gas
gonna
is
smell that oil.
flammable?
You will, huh?
Is it because gas is also flammable as well?
No, the flammability, remember, that's a chemical. These are all physical. Yeah, that doesn't have anything to do with the actual chemical reaction. Although the fact that gasoline is so readily going into the atmosphere for that vapor pressure, that's one of the reasons why it makes those, it's very easy to light up, because while oil does want to burn, you can pour gas on the ground and not even get the match all the way to it. You'll ignite the fumes. You won't ignite the fumes of oil.
Okay.
Hey,
Yes,
Forrest.
April, yes, we are. It's coming right up. I'm almost there.
Real quick question on this, Forrest. You're saying, are these all higher? Or I think I'm missing, like, when you're saying it's stronger or it's why it's stronger, is it you had higher BP and then I have
Stronger is higher.
viscosity? So wouldn't the last one be higher viscosity,
Say again?
lower vapor?
Yes. So why don't I go and say higher viscosity, lower vapor pressure.
Okay, and the others are all higher.
Yes. Remember, vapor pressure is the only one that's off.
That's lower. Okay.
So a couple things to take away from this is you may not know what those intermolecular forces are. I mean, for Pete's sake, pancake batter, I don't even know what's going on there, but I do know that overall it has higher intermolecular forces because of how thick it is, because of how viscous it is. When you look at any of these pairings, you want to just think physically, am I going to smell it first? Is it thicker? Is it more viscous? Does it take more energy to boil it? So any of the questions that I can ask you are going to be related to that, in that you can just use your own life experience to basically figure that out, even if you don't know what they are. Does that make sense? I love silence. It means yes. All right.
Yes.
Finally, let's do the last little thing. And that is the heating curve. This is kind of fun. Oh man, can I write a little better? Now, the heating curve is kind of a cool little thing. I'm going to go ahead and draw it and then label it. Oh wait, I have this. Oh yeah. You like that? I just made perfect lines. Did you? Do I have other shapes? Can I do lines? Oh. Well. Oh wait, undo. I have to get it each time. All right. So what I'm drawing here is the generic form of the heating curve. And apparently not quite getting them connected. There. And on the left-hand side, what I have is the temperature in Celsius. And on the bottom, I have the amount of heat that I'm inputting into the system. And there are some places that I want to label on here for you. And that is this one right here. This is the melting point. And the other one is the boiling point. Now, I don't care what those numbers happen to be. Those numbers can be whatever they are. If they're water, we know they're 0 and 100. If they're alcohol, they're significantly less. I think alcohol boils at like 78 Celsius or something like that. And it melts clearly lower than water. But this is the general form of the heating curve. Now, what this looks like is as follows. Down here, this area right here is where you have a solid. If you put more heat into a solid, you will make it hotter. Duh. The next one on the lines here is the following. We've got the liquid, and finally the other ramp is the gas. Each one of these in these phases is, as we increase the heat, we will increase the temperature of that system. Here's where the fun part is. We're almost done there, Reagan. I have to use the facilities too. I'll be a little faster next time because we won't spend half an hour doing the other stuff. I do apologize. We have these other two things to consider, and that is these transitions here. We have one going that way and an arrow going backward. So can I fix you? I think I just have to make these bigger here. And the following. One going this way and one going this way. Now, these are when you're going from a solid to a liquid. Let's set the way back machine. We know what that term is called when we go from solid to a liquid. What is it?
Melting.
Melting. So if we're going up the curve, as it were, when we're going from solid to liquid, that is melting, which means if we're going backward down the curve, liquid to solid is?
Freezing.
Freezing. And liquid to gas was?
Vaporizing.
Vaporizing. And backward, he said, was condensing, right? Now, the thing I want to point out about this in the heating curve, and this is something that is often lost in translation or just lost in the shuffle, as it were, we can agree that if you take a solid and you put more heat into it, you make it hotter, yes?
Yes.
Okay.
Yes.
If I have a liquid and I put more heat into it, I make it hotter, yes?
Yes.
And we can obviously
Yes.
make a gas hotter, yes? Well, what is happening at that, nice, Sume. Sume said, we. Oh, no, it's Kimberly, sorry. What happens right there at the melting point and at the boiling point? Are we not putting more heat into the system?
No.
Yes, we are. You see that I put this line here and I said, hey, we are going to continue to put heat into that system. We're putting more and more heat, yes?
Yes.
Yes.
So,
Yes.
what's happening at the melting point then? All of the energy we are putting into that system is doing nothing to the temperature. I want you guys to think about that. You take a solid, you put more heat into it, you get hotter, yes?
Yes.
Yes.
Yes. Same thing with a liquid and a gas. But what happens to the temperature once we reach the melting point? It does not go anywhere. What's the temperature when we reach the boiling point? It goes nowhere. Does Why is that so important? Well,
Phase changes.
yeah, the phase changes. If all we ever did when we put more heat into the situation, if it just decided to willy-nilly jump from solid to a gas, we're in a big world of hurt. The whole reason our planet doesn't just, boil away or something is those oceans can suck up a lot of heat as the sun is trying to boil them off. They're like, yeah, how about no? When it's trying to melt the ice caps, the temperature goes, yeah, how about no? You're going to take a long time before you just instantly turn me into a liquid. If we take a look at this on a physical level, it's going to start getting hot these afternoons, and we're going to go get ourselves a nice icy soda when the lockdown is rescinded, and we're going to put ice into our cold drink. An hour later, our drink is still going to be cold as long as we have ice in there. And that's because all of the heat from the atmosphere that is trying to warm up your glass to room temperature, it hits the liquid goes, I want to heat up, and the ice is like, I got this, step off. You give me all that heat, I'll take it, and I'll start to melt. And guess what? We're going to stay icy cold until I'm gone. We put liquid into our ice cube trays. Do you remember those things, ice cube trays? You had to fill them up and put them in the freezer to make ice before we had ice machines. Anybody?
Yes.
Yeah.
Yes.
Did it instantly freeze? No.
No.
It took a while. Why? Because all that energy is going into freezing, and so it's going to take some time. The same thing with cooking pasta, right? It takes 10 minutes to cook pasta. Why? Because we know that at 100 degrees, it takes 10 minutes to cook pasta. Go to Denver, Colorado, where water boils a lot less. It will take you 14, 15 minutes to boil the pasta. That's because it's boiling at a lower temperature. Thankfully, too, when we reach the boiling point, all that liquid does not immediately turn into a gas. All that heat we're putting in is busy trying to vaporize it, but the temperature does not change. If it did, we would have no way of figuring out how to cook stuff because the temperature would always be moving. Guys, remember when we did the boiling point of methanol? We didn't actually measure the boiling point. We measured the condensation point. Remember, those vapors were hitting the cold thermometer and making it hot.
Okay.
The vaporizing and condensing point are lo mismo. So you'll want to be able to draw one of these and label it and sort of explain it on an exam when we get there. This is essentially the end here. Do I have any burning questions? All right, hearing none. I'm going to go ahead and stop the recording, but I'm still going to talk to you guys here. Where's my recording? How do I stop recording? Well, that's weird. Oh, stop recording. There we go. Do I want to stop cloud recording? Yes.
Did you just